Okay, let's reconvene for our afternoon sessions. We'll be starting out. We've heard about the measurements that are needed, and now we're going to hear about present capabilities.
This talk right now.
So we're first going to hear from Devon Burr and Claire Newman with a focus on aeolian meteorological. And then we'll go over to Gérman Martínez, who will talk more about liquid, ice, volatile interactions with the regolith. So, all right, go ahead, Devon.
Thank you, Serena. Hi, everyone. So I've pasted in the description of this session this afternoon that I'm leading off on. And I've underlined what I'll be talking about, the laboratory measurements. Of course, we got to hear about analog field studies on the prior session and from Cynthia earlier this morning. And then we'll get to hear about planetary in situ measurements from Claire. All right, so I'm going to base the first half of my talk on a planetary science and asteroidal decadal white paper. And the executive summary of that white paper is below. I'll focus on the 3 or 4 last bullets and sort of use the executive summary for each one of those bullets as the title for each of my next 4 or 5 slides, and then move forward in time as to what's happened since then. So this audience knows well, probably, that the use of wind tunnels has provided fundamental insights and quantification of aeolian processes, that wind tunnels simulate airflow interactions with the surface that can give us information about bed forms, as well as the physics that's happening there, as Tim talked about earlier. Terrestrial boundary layer tunnels have been used for 80 years now or more, and give us an understanding of fundamental parameters such as threshold or saltation trajectories. Here's the wind tunnel from the 1930s and 40s used by Ralph Bagnold. And here's some saltation trajectory information, so ingeniously collected using backlighting. The use of ambient, and I'm using the term ambient here because planetary seems a little bit, Earth is a planet also, but ambient boundary layer wind tunnels have provided fundamental insights and quantification of these processes. Just on the previous slide, I've listed on this slide a few different wind tunnels that have ambient conditions that are located around. On this slide, they're all somewhere in North America. I'd like to highlight the 4th bullet. Trent University in Canada has a Trent Environmental Wind Tunnel that has particularly nice environmental control. So they can get down there to -10 Celsius and they have full humidity control. Every one of the wind tunnels on this slide provides really nice instrumentation and capabilities for ambient conditions. There's a planetary wind tunnel specifically designed to simulate Mars processes. So the Mars Simulation Laboratory at Aarhus University across the pond. There are actually 4 wind tunnels as part of that laboratory. So 2 are open circuit for sand transport and 2 are closed circuit wind tunnels. And they enable simulation of low Mars pressures for surface experiments. So you can see at the bottom of the slide there that the temperatures here go down to -60 as opposed to -10 on the previous slide. And there are a number of other really nice control parameters, boundary conditions that can be set, not only temperature, but also pressure, gas composition, humidity, and of course, wind flow. Back on this side of the pond, out in California, the NASA Ames Planetary Aeolian Laboratory is a unique wind tunnel facility for simulating extraterrestrial aeolian processes. On the far left, that image is of the vortex generator in the Planetary Aeolian Lab. The middle image shows the vortex generator at the top of the photograph. And then in the middle of the photograph is the Mars surface wind tunnel. And then the lower right of that middle photograph is the Venus wind tunnel. And then the image on the far right shows the Venus wind tunnel, which has been used most recently for Titan work. The bottom text on this slide gives some of the unique advantages of PAL. And again, this is from not only the white paper, but from a study that was done half a dozen years before, published in 2015, when there was a review of NASA facilities. And that study, those panel reviewers found that PAL was uniquely capable of large volumes of air at low pressure. With the Venus/Titan wind tunnel, PAL could also provide high pressure conditions. It did have older instrumentation and it had some limited control of conditions compared to international wind tunnels, which have a smaller volume, such as in the Mars Simulation Laboratory that we saw in the previous slide. There's no high pressure simulation for aeolian conditions that I'm aware of overseas. In comparison, the international wind tunnels have rather more modern instrumentation and better temperature and humidity control. So again, speaking from the comments provided by this 2015 NASA facilities review, PAL has these unique strengths of large volumes at low pressure. The panel review did advocate efforts to solicit wider utilization. It was pretty localized at the time. On the right of this slide here, you can see where I've listed some of the subsequent developments since that review half a dozen years ago. So there does seem to be wider utilization of the PAL facilities today. It seems perhaps that those users are localized in the San Francisco Bay Area where PAL is located. Regardless, there's more utilization today perhaps than in the past. Some of the weaknesses that were addressed by this review are a lack of transparency in management. There were some barriers to use, such as just getting on to NASA Ames, which is challenging if you have international colleagues or say students from overseas that you're trying to involve in the work. And there weren't obvious avenues for training in this facility. Some of the risks were staff overturn. To use the Mars surface wind tunnel at low pressure, there needed to be some coordination with the steam plant, which meant that drawing down to low pressure and the duration of experiments at the low pressure was somewhat challenging and uncertain. There were suggestions from that facilities review, and that included having research scientists with an active interest in wind tunnel work co-located with PAL. I understand that Don Banfield is now at Ames or moving to Ames, which is terrific, and that there were improvements needed and that those would be best decided upon through a committee that operated with committee input. And I understand from Ken Smith, who is the PAL engineer, and from other workers presently doing experiments in PAL, or at least since it opened up again after the last couple of years, that there are some improvements there, such as a new camera, other things. Here are a few more pieces of information about the PAL user experience or issues since that SMD facilities review. There seems to be a somewhat limited understanding of or information on the turbulent structures that are developed in these wind tunnels. More modern wind tunnels have non-invasive instrumentation that responds more quickly to turbulent structures. In contrast, the wind tunnels in PAL have pitot tubes that respond relatively slowly, so we might be missing information. Other instrumentation is also somewhat limited. Don't know much about sand fluxes or grain trajectories in there. And then both a paper from a couple of years ago and a paper just from last year note that it's hard to understand just how well the wind tunnels can simulate some aspects of aeolian behavior. It seems like both for the Titan wind tunnel and the Mars wind tunnel, that thresholds can be measured perhaps with some degree of fidelity to real life, but that beyond that point, maybe there's a challenge simulating anything beyond getting the grains off the surface. So here's some recommendations. Those are from the white paper, and I'll turn it over to the next speaker. I won't take time to go over those.
Oh, thank you very much, Devon. Claire, I think you were going to share your screen as well.
Yeah, and I also, in the interest of bandwidth, will not share my video until we get to the discussion. Okay, can everyone see that?
Yes, it's up.
Great. All right, so I have a lot of slides in here, and I'm sure there are far too many, and but I will try to record a sort of longer version of this talk for YouTube, and hopefully some of them we can go back to during the discussion if people want to talk more. So these are some nice results from Gale Crater and Jezero Crater, showing some dust level movies and wind gusts being lifted. Obviously, Mars isn't the only place where we have in situ meteorological and/or aeolian data. I wanted to be clear about that. But Mars is going to be my focus in this talk due to the many missions and data sets, and also a severe lack of time, because I think it demonstrates many of the issues that have come up already and will continue to come up in terms of what we need to send to other planets to understand things better. So there have been 10 Mars surface missions that have returned meteorological or aeolian data, including the recent Chinese mission. And so this is a summary of all of the main meteorological instruments that I'm aware of on those different landers and rovers. As you can see, as we get, and they're in chronological order here. So as you get more recent, and especially the larger, more recent missions, so for example, MSL and Mars 2020, we're looking at having, increasing numbers of sensors doing increasingly complex measurements, or a wider range of measurements, at least, with some interesting additional sensors, especially in the aeolian side of things. And then I should say that all of these missions were able to do some meteorology via imaging, and also aeolian stuff via imaging. I should have made that clear as well. For example, measuring the aerosol optical depth and sizes, and cloud tracking, obviously dependent on the camera quality and so on. So there are some key issues, and I can't possibly go through all of them, but some of them that relate to Mars and relate to these kinds of measurements involve better understanding or predicting what Martian weather and dust storms, and also interpreting surface changes, because what's going on with the weather and surface interactions is the main driver of surface change on modern day Mars. So basically broken these things down into some key categories. Category A, how well can we predict weather in advance? And part of that comes into, can we validate atmospheric models with the existing data, which includes a lot of the in-situ met data? Do we have in-situ surface met data that we can assimilate into models to do sort of better weather forecasting the same way we do on Earth? And how important is dust in controlling weather and climate variability? And the answer is very on Mars. And so that brings us to our next big issue, which is, how do dust storms initiate and in some cases grow to become global? And you really need to know three things to understand this. First of all, you need to understand the processes by which dust is lifted. So that means connecting the dust flux to local conditions. So obviously, to understand that, you need to measure both sides, the local conditions and the dust flux. We need to know what are and then you can know the processes perfectly, but if you don't really know what the atmospheric conditions are across Mars, which you can only know that globally from a model, then you're not going to do a great job of predicting dust storms or understanding them. And so again, you need good models, which brings us back to point A and being able to validate the models using in-situ data. And then the third thing you need is to know what the surface properties are and how they vary across the Martian surface. So that isn't just maps of surface roughness and so on, although that's really important. It's also what's the dust availability and the sand availability as well, if in case, siltation-driven dust lifting is really key. So that brings us on to, what controls surface changes on Mars. And again, if you don't have good models of, say, winds and that kind of stuff, then you're not going to be able to really understand that fully. So how is dust rearranged in and outside of storms? Well, then you need to understand how storms develop, and how dust is lifted. What controls is location, orientation, and motion of sand dunes? What controls location, orientation of yardangs and other erosional features? And other things like RSLs, are they driven by dry process or by a combination of wet and dry? So wind data are also crucial to Mars exploration in the sense that they impact things like entry, descent, landing, and phase of emission, as well as to those meteorological and aeolian investigations and topics that I just talked about. So surface atmosphere exchange, dust lifting, dust storms, and modern surface changes. So I'm trying to make the point here that unfortunately there's a long history of problematic Mars wind measurements. And so it's these kinds of things that we need to be aware of and hopefully do something about in the future. So this is a list, the best I could make, of those same missions I showed before, and now focusing on the wind sensors. And the key column is really this fourth one, which is whether that wind sensor was still working by the end of the mission. And unfortunately, the most recent sort of big missions that have been in places where there's been moderate or strong aeolian activity, the wind sensor has been badly damaged. So I'll come back to that later. We've also had a history of having missions with no wind sensors. We've had missions where there have been mechanical wind sensors, which have in some ways been more reliable, but in other ways, those measurements are made by imaging, the telltale or the windsock. And so that by definition means low frequency and a reduced accuracy of the measurement. So just a really quick tour through some of the, not all, but some of the wind data sets. Viking Lander 1 and 2 did provide useful wind data. Viking Lander 2 provided it over probably the longest time period, almost 2 Mars years, but they mostly did not have high frequency wind data. In-Situ has actually provided the most complete Mars wind data set to date, I would argue. There's these 2 wind sensors mounted on booms, and you need 2 of them so that because things on the lander are going to impede the flow coming from one direction if you only have one of them coming from sort of behind the sensor. So you need 2 sensors so you can measure the flow from all directions. And then this just shows the seasonal wind variations at a fixed location every 1 Mars year. These are 3 hourly means and daily means and wind speed and direction, just to give you a sense of this great data set. We also were able to look at the impact of a regional dust storm on wind speed and direction. And so basically there are reliable 1 Hertz data that are taken continuously for over a Mars year. So I'd argue this is the most complete wind data set from Mars to date, but unfortunately, there's limited aeolian activity at this site to correlate with. And so we only really have imaging and some solar array current data to kind of shed light on what was happening in terms of dust lifting or sand motion. The most recent rover for NASA rover, Mars 2020, was able to provide wind data and had a lot of aeolian activity. So it's very valuable for that reason. And these are some of the wind data, some diurnal cycles of wind speed and direction. These are some wind gusts that were measured, and these were also corroborated by strong signals in the microphone, the SuperCam microphone. And these were very close to some big wind gusts, so a lot of aeolian activity. Gust-driven dust lifting events. So now we have reliable 1 Hertz wind data taken continuously for more than a half a Mars year, and it can connect to aeolian geomorphology, sand movement, and dust lifting events. So this may be the most useful wind data set from Mars to date in terms of understanding such links. But unfortunately, the downside of having all this aeolian activity is that we've had some damage that may be terminal to these wind sensors. And now, okay. I may need a couple extra, I'm so sorry. I'll do my best though. So Mars Pathfinder was the only mission though so far that has measured wind as a function of height and therefore was able to extract the surface roughness and friction velocity and hence get a sense of the wind stress. And so I think that is a key point here, that is the really crucial thing for understanding thresholds for motion and understanding what drives the fluxes. And we've only measured that once and only a handful of times. And as yet, no mission has returned vertical wind speeds or wind data at better than 2 Hertz frequency. So there are obviously all these problems with trying to understand 3D turbulence, measuring U-star directly via eddy correlation, and measuring things like sensible heat flux or vertical tracer fluxes. And I know Gérman will talk more about this later. Quickly going through aeolian measurements, these have typically relied on imaging, and so they've generally been more qualitative than quantitative. The Viking landers were able to demonstrate they didn't see much change except for during a dust storm. Sojourner rover with the Pathfinder mission saw some nice dunes. Spirit rover saw some shifts in ripples, some changes in ripples, and a lot of aeolian activity, including dust devils, and Opportunity saw those as well, but sadly had no wind sensors or pressure sensors. So they couldn't really relate that to atmospheric conditions. And MSL, unfortunately, only imaged significant sand motion after we lost the final wind sensor. However, we were able to, from those images, identify at least that the most of the motion was happening overnight and in local spring and summer. And then In-Sight was finally able to relate surface changes to vortex pressure drops and wind speeds. And this is from Mariah Baker's paper. Although unfortunately, most of the changes were pretty small, although perhaps that was good for the survival of the wind sensors. And then with Mars 2020, we have both an active location and the best set of sensors to date. And I just want to finish by talking about some of the novel dust measurements that we've been able to make with 2020. So we have these photodiodes that look up from and around the rover, and that lets us do things like track dust levels around the rover, whether you can see an increase in the scattered shortwave, and also, you can see the decrease in downward shortwave as the dust level is in sort of the area. And they can also, and this is a really cool result, there's 2 different sensors on the rover that can measure both the downward and the upward the reflected sunlight. And so that's able to give a measure of albedo and therefore the surface dustiness. And so what that means is that you can actually immediately see when a dust level, in this case, that passed by the rover, was able to actually reduce the brightness of the surface and make a persistent drop in albedo. And that was related to, dust lifting. It had to be. So this is where we can produce some dust level statistics, where we can relate dustiness to pressure drop and wind speed, and also whether dust was lifted locally or not. And so I have all these slides about limitations. Serena, do I have time do I have 1 more minute to go through these? No.
Very, very quickly.
Okay,
Yeah.
really quickly.
Yeah.
I'll touch on the high points. So
Excellent.
limitations of the current data sets and sensors. I think a big one is the poor accommodation of especially thermal and wind sensors and wind sensors. And so that means, lower accuracy, they're sensitive to the time of day or the wind direction and impacting the thermal data. And also an inability to measure 3D winds. And this is an example of how the wind really gets messed up when it goes around this mast. So that's the last place you'd want to put wind sensors. And unfortunately, that was where we were kind of condemned to have them. And then susceptibility of damage of some wind sensor designs is worrying. And it's especially problematic that it happens when you have a lot of aeolian activity around and grains being carried in strong winds or vortices, or with active sand dunes. And sadly, these regions are the most interesting. So here's some other points. One of the big ones, obviously, wind stress data is really lacking. So motion thresholds, because I think it's important to bear in mind, wind stress is the key thing, not U star or wind speed, but wind stress. And you can't find those thresholds of motion. And then here's my summary. I won't go through it in great detail, except to point out that other contributors to aeolian activity, such as electric fields, have not yet been measured. We have made some improvements, I think, in terms of dust sensors recently, but we're kind of not making as much progress when it comes to wind stress and winds and dust lift and connecting the dots. And so I think the takeaway for Mars is, if weather and dust prediction are really key to human mission success, then NASA should not just fund the development of sensors, but must also fly more sophisticated sensors and better accommodate them in order to make progress. So sorry for going over, and thanks for listening.
No, thank you very much, Claire and Devon. As you all can see, I gave them a Sisyphean task of tell us all about what's been happening in 10 minutes each. So Herman has a similar challenge. Herman is going to be sharing his screen. Excellent. And go ahead.
Can you hear me, and can you see my screen?
Yes.
Okay. So thank you very much. This is Gérman Martínez from the Lunar and Planetary Institute. First of all, I want to thank the organizers, and I want to thank the audience for being there. So the title of my presentation is Present Capabilities and Results in Planetary Surface Volatile Investigations. But similarly to what Claire did, I'll focus on Mars for 2 reasons. Because we have many data sets and missions, and also because this talk the one that I'm giving is supposed to complement the one that Edgar Rivera-Valentin and Katz Williams gave before. They talked about the needed measurements to increase or to advance our knowledge on regolith atmosphere interactions. And here, what I will do is to show basically current measurements and current lab experiments and what we know based on current capabilities. So moving to the next slide, here on the left, what I'm showing is that water vapor exchange between the surface and the atmosphere can take place as a result of physisorption, also called adsorption, desorption, salt hydration, also called chemisorption, brine formation, and frost formation. So these processes strongly depend on the regolith temperature and the surrounding relative humidity. And the reason these processes are very important. Oh, sorry, is someone talking or? Okay, I'll continue. So the reason surface atmosphere water exchange is key is because it has a strong, it strongly affects our understanding of the present day Martian water cycle. And this also in turn affects the current climate. And as an example, imagine basically if we knew better the amount of water vapor at the surface, this could better inform us of the stability of near surface water ice. And this is just an example of how this knowledge can impact, like the present water cycle and the current climate. It's also important for brine formation and related habitability. Edgar went over this before. These exchanges are definitely important for planetary protection, ISRO, and sample return. However, this exchange remains a major unknown. This is very well summarized and captured in the white paper led by Edgar Rivera-Valentin. And in the remainder of this presentation, what I'll be doing is why this role remains a major unknown. First of all, based on current in-situ measurements, and second, based on current lab facilities and capabilities. So let's start with the in-situ data. And let's start with the good news here. So as I mentioned in the previous slide, ground temperature and relative humidity are key quantities to understand these processes. We have measured atmospheric relative humidity and ground temperature for various missions. So on the left, in this figure, you can see the landing sites of all the successfully landed missions on Mars. And on the right, you can see a similar table to the one Claire showed. But here, what I am highlighting is whether these missions included a weather station, and most importantly for this talk, whether they included a relative humidity and a ground temperature. So what you can see is that the Phoenix mission was the first mission including both a sensor to measure relative humidity and ground temperature. MERS only measured the ground temperature. Then the MSL included both quantities, and same thing for the Mars 20 and 20. So let's take a deeper look at how relative humidity and ground temperature look for these missions. So here in this slide, I know it can be a little bit overwhelming, but let me walk you. So this slide is showing all the relative humidity data set measurements ever measured from the surface of Mars. So let me start with the first column and the Phoenix mission. So on the top left, you can see the coverage of this mission. So you can see the sol number as a function of as a function of local true solar time. And what you can see is that the coverage was patchy. So we didn't have like complete diurnal coverage for the Phoenix mission, which by the way lasted 151 sol. So with this coverage, it was good enough to analyze the relative humidity in diurnal time scales. And that's what I'm showing here on this figure. So we knew that the relative humidity reached saturation levels at 2 a.m., that it was close to zero during daytime. And so diurnal studies can be done with this data set. As for the seasonal evolution with Phoenix, we lack, we don't have that precision because of the patchy coverage of the Phoenix. Now, moving to the MSL, which is the middle column, here on top, I'm just showing an example of the measuring cadence. But the important point of MSL is that now we have continuous measurements, or at least we have like every single hour of the day, every sol number is covered. So MSL is providing these continuous measurements for the first time. As an example here in the middle, I'm showing the relative humidity as a function of LMST for 3,500 sols. And don't want to get into the details here, but it's just so that you know differences in coverage and what each mission can allow us to investigate. With this kind of continuous coverage, MSL also allows for seasonal evolution and seasonal studies, and that's what I'm showing here at the bottom. And then finally on the right, we have Mars 20 and 20, and it's similar to MSL. So we have continuous measurements, and we can analyze relative humidity both diurnally and seasonally, which is what I'm showing here. Okay, so that's relative humidity. What about ground temperature? So once again, here I'm showing, to my knowledge, all the ground temperature measurements from Mars. And let me start with MER-B and MER-A. So here, these two figures. So what you can see is that this provided the first measurements of ground temperature, but as you can see, the nighttime period was badly covered. There were only little instances when ground temperature was measured by MER-B and MER-A. Then the Phoenix mission here on the right provided the first like diurnal coverage of ground temperature, but only for a few sols. Indeed, these were like, I think 3 or 4 sols, if I will remember. So now we've gone better. And if we go to the bottom row, what we can see is values for the MSL. And again, here I'm showing all the values for the first 3,500 sols. And you can see that now this is great because we have continuous measurement, day-night, daytime, nighttime. Same thing for the insight here in the middle, but obviously the insight was a lander. It was not moving, and that's why you have sort of this behavior. Finally, on the right, you can see all the Mars 20 and 20 ground temperature measurements. These are still, you know, like being measured. Same thing for MSL, and we also have continuous measurements. So, okay, I've shown the ground temperature and relative humidity, which are our actual observations. But what about the absolute water content? I'm sure you are familiar with papers that have shown these values from different missions. But I want to make the important point that this quantity, the absolute water content, has not been measured on Mars. We are estimating this quantity from relative humidity and temperature measurements. And this is important because uncertainties in the derived VMR values might be large due to propagated uncertainties in relative humidity, temperature, and pressure. And this is what I'm going to show in this figure. So once again, to my knowledge, this is the complete data set of volume mixing ratio estimations on Mars. And let me start with the Phoenix, with the left column. And the coverage, I already introduced this figure. So if you take a look at the middle figure in the left column, here we can see the volume mixing ratio as a function of the local mean solar time for all the sols of the mission. And as you can see, we have we have the diurnal period well covered. We cannot do much seasonal evolution studies because of the patchy coverage, again, because we don't have, we cannot obtain diurnal averages because we don't have complete average, right? Now for MSL, which is in the middle column, this is when it is important to understand that we're not measuring VMR, but estimating that. The VMR values that we can estimate from relative humidity and temperature measurements from MSL are only accurate enough at about 6 a.m. when the error or when the accuracy in relative humidity is the highest. So we do not have diurnal information about MSL. We do have seasonal, but seasonal only using the value at 6 a.m. Now for March 20 and 20 here on the right, we are in a better position because the VMR values cannot still be obtained during daytime with enough certainty. That's why you have like this lack of like blank space, but they are accurate enough during nighttime. So we are in a much better position than with MSL. With Phoenix, we had the diurnal coverage, but we were lacking, seasonal or interannual information. But with MSL and March 20 and 20, it's the reverse. So this is the status of all the measurements that are important to understand surface atmosphere exchanges of water vapor. Now, how have all these measurements and values, how have they been used to inform the community about, these processes? So what I'll do now is to show you how all these measurements have been used to address phase absorption, changes in the hydration state, frost formation, and brine formation. So let me start with brine formation analysis. And here I want you to know that I'm showing sort of summarizing or representative research. There's many people working on this, but hopefully this captures the essence of all these investigations. So in this figure on the right, I'm showing the temperature and as a function of relative humidity over water. And all the colors represent measurements at the MSL and Phoenix landing sites. Then the dust colored lines represent the liquescence relative humidity for calcium perchlorate, magnesium perchlorate, and sodium perchlorate. So as Edgar explained before, for the liquescence to happen, for a brine to form, ideally we would like all these colors to be, to be on the left from these dust lines. But we barely have that overlap, maybe at some point during a few minutes on a certain sol, we might have conditions compatible for brine formation. But would kinetics allow for this? We don't really know if during those 5-10 minutes where conditions are favorable, brines would form. So again, from current data, we can say, hey, yes, conditions are favorable or not favorable for brine formation, but we cannot really tell whether brines formed. So moving to salt hydration, we have a similar problem here. So on the right, I'm showing again the ground temperature as a function of relative humidity with respect to ice. And in this case, I'm showing values for the March 20 and 20 mission, which by the way are very similar to MSLs. But what you can see here is that our values, the lines, the black lines, by the way, represent stable and metastable boundaries for changes in the hydration state of certain salts. And what you can see here is that, yeah, based on our data, it seems that during the course of the day, these salts might undergo changes in their hydration state. Like it's possible, but once again, would kinetics allow for this? If these transitions occur for 10 seconds or 10 minutes, is that enough time? We don't really know. Let's move now with adsorption, the other process to exchange water. So here on the right, what I'm showing is the volume mixing ratio as a function of LMST. And the triangles are estimations from March 20 and 20. So these are estimations. And then the solid black lines are simulations with a model that included an adsorptive regolith. So basically that included adsorption, desorption in the regolith. And the interesting thing here, you can ignore the I300, 400, and 600. The interesting point here is if with the model we don't consider adsorption, that's the dust line, then we cannot get a good fit to the estimated values of BMR. So we need to include an adsorptive regolith to be able to match these values. So this is telling us that adsorption is very likely taking place on Mars, because this happens for Mars 20 and 20, and same thing for MSL, Phoenix, and Vikings, and every mission. But once again, like, these models are assuming that desorption is instantaneous. So would kinetics allow for this rapid exchange? That's something that we really don't know. Finally, the last process is frost formation. And this one is simpler. Here I'm giving two examples of how we have studied frost formation on Mars. On the left is a straightforward example, because it's basically, okay, we took an image, we take a picture, and we saw the frost. So the left figure, this is Viking 2, and the right figure, this is Phoenix mission, and hopefully you can see the frost. On the right, what I'm showing are interesting results for the MSL mission. So for the MSL, we have not imaged frost. We have not. But we can predict, or we can identify frost formation by combining environmental measurements and ChemCam LIBS measurements. So on the left figure, what I'm showing is that using environmental measurements, the ground temperature fell below the frost point between 4 and 6 a.m. on a certain sol. So this is indicating a potential frost event. And interestingly, contemporaneous measurements taken from the ChemCam LIBS, measuring the hydrogen content, showed an increase in hydrogen content right at that time when we predicted frost formation. So this is likely suggesting frost formation on Mars. It's not for sure, but it's likely. And again, this has not been imaged. Now moving to the lab experiments, and this is the last slide before the conclusions. So what I've shown until now is the typical studies that have been done using in situ measurements to address surface atmosphere exchange of water vapor. And I've shown hopefully like what we've learned and basically what was unknown. Now I'll focus on lab experiments, and lab experiments are obviously another way to increase or to advance our knowledge on this exchange of water vapor. But something that I think it's important to highlight, and this was also like stressed by Edgar in the previous session, but although previous experimental work has definitely improved our understanding of H2O exchange between the surface and the atmosphere, it has been mostly conducted outside of Mars relevant conditions, and that's shown here in this figure. So in magenta, you have like pairings of relative humidity and temperature values used in previous lab experiments. And again, these are greatly summarized in the white paper by Edgar. And what you can see is that these magenta values are not quite inside the Mars relevant cyan space. And I want to make the clarification that it's not that previous, like laboratory investigations were not aware of this. Like, indeed, I am one of those magenta circles, or my group. What you need to understand is that it was only recently, it was only in the last years of the last decade, so 2017, 18, 19, that we started to have combined measurements of ground temperature and relative humidity, because the Phoenix relative humidity were recalibrated and finally made available in 2019. The ground temperature from the relative humidity had issues. So what I'm saying is, like, in situ data have been made available to the community in the last few years. So now it's time for experimental people like me and others to catch up and basically to push down all these magenta colors. So in conclusion, this is the first slide having to do with current knowledge. So up to now, we have used measured values of atmospheric relative humidity and ground temperature. and estimated values of water vapor content to investigate exchange of water vapor. And this has been done in combination with modeling. What we have learned is that it seems clear or extremely likely that adsorption-desorption must be accounted for because otherwise models are not able to match estimated values. So we really need adsorption-desorption to take place on Mars. What about the other processes? So changes in the hydration state and brine formation might occur based on our environmental measurements. But again, the kinetics of this process remain unknown at current conditions. And in terms of knowledge gaps, but this was better covered by Edgar and Kat Williams, but I think that laboratory experiments at like lower temperature and relative humidity are needed to constrain kinetics of these four processes, because again, we want to understand these four processes to characterize the water cycle on Mars, and therefore climate, brine formation, ISRU, planetary protection, etc. In addition to our current observations of relative humidity and temperature, just 20 seconds. It would be ideal to have high frequency contemporaneous measurements of water content and vertical wind speeds at various heights so that we could measure fluxes, but this has been covered in previous talks. And like with our current measurements plus these two first bullet points, I think that we would be closer to answer the outstanding science question of how much and how rapidly water vapor can be exchanged between the surface and the atmosphere. And thank you very much.
Excellent, thank you. We are now moving into the discussion period. James, did you want to say anything as our online chair?
Thanks, hopefully you can hear me. Yeah, so there hasn't been a lot of banter in the chat here online. I think people hopefully are just holding their tongues, waiting to discuss the next points coming up, Srinath. So that basically leads us into the discussion, trying to finalize a handful of investigations that we believe require in situ measurements based on the demonstrations of what measurements exist currently, also what analog measurements are and instrumentation are available. So I invite, after thanks to the speakers just now, I'd like to invite everyone to make some suggestions either in the chat or coming forward by turning on their microphone.
Not yet, Brian. Yeah, that's the next period. All right, so this discussion period, you have a chance to ask questions of the previous presenters, and as James said, thank you very much to all of them. One of the main things we need to walk out from in the next 12 minutes, though, are about 4 investigations that we would want to focus our discussion periods around, because as we divide into the small groups, we thought we'd divide that way. So I can lay out my favorite ones, but let's see what others think first.
I don't want to speak because I can see, because I already spoke a lot, but yeah, Don just posted in chat actually, dust lifting is key unknown for Mars because so many different things come into it. So it's not just measuring the dust flux, it's understanding siltation and the link between siltation and dust and electric fields and potentially even water and cohesion and the surface properties. It has so many repercussions when it comes to understanding the Mars climate system and surface changes.
So just to add another point that's been, there's a couple of points brought up. So Joel has written that perhaps that's been underutilized or talked about, although it's been widely used in terrestrial environments, is topographic change detection. And this probably goes back to Serena's presentation as well, talking about roughness and its importance not only for dust uplift, but obviously affects things like water balance and latent and sensible heat fluxes as well.
And I apologize, I had to miss some of the earlier talks, but could you talk a bit more about topographic change detection and what comes into that?
Sure thing. This is Joel. Yeah, so I guess it's just I'm relatively new to this kind of Mars geomorphology world. I do lots of geomorphology research here on Earth, and one of the key tools we use is just topographic change detection, whether it's from photogrammetry, right, derived from whether it's satellite imagery, airborne imagery, ground-based imagery, LiDAR, other topographic surveying methods. And we use that a lot for terrestrial geomorphology work, kind of within the, I guess, the discipline or technique of morphodynamics and looking at changes in, aeolian bed forms or fluvial bed forms, for example. And from that, you can actually infer sediment fluxes. So it's another way to be measuring sediment fluxes that is really utilized as kind of an alternate or additional method on Earth that I think could be used to a much greater extent on Mars. Just because there is satellite imagery, there are digital train models that are derived from photogrammetry.
I mean, there's certainly that, the DTMs and comparing them and things like COSI-Core have been used, to look at changes and flux measurements in dunes. And I think it would be awesome to do that to a finer level. I'm not sure how the application of that on Earth is different to the application on Mars, whether Earth you have finer precision or there's just more repeats of the same, bed forms and things like that, because that's one of the problems. Obviously, you can't sometimes have to wait our turn to look at things with, only perhaps one instrument that can really see at that high res.
Yep. Go ahead.
Sorry, clarification on that one. Topographic change, what I'm hearing described strikes to me is more like an orbital investigation, or is this something to investigate in situ?
So, yeah, I mean, we certainly on Earth, right, we do that from, say, satellite observations, digital train models derived from imagery, right? Whether it's satellites or near surface airborne platforms, drones. But there's a whole component of that that's done on the ground using ground-based sensors that can be either operated by a person on Earth or autonomously on Earth and other planets.
Yeah,
Sorry, go ahead.
Us Jack Gillies, I like to comment as well. I think one of the things that we should keep in mind is that something like Ingenuity has opened the idea for paired systems on Mars. And if you can get DEMs, local DEMs of the actual physical roughness of the surface where you are, that also then adds a huge layer of information to feed the process side of things. You can, if you get the digital elevation model, then you can do things like change detection, but it also would help alleviate some of the uncertainties about things like Z0 or what is the lambda of that surface, so you can do shear stress partitioning. So although we talk about, making a sensor or our particular sensor, I think when you look at the current thing on Mars where you have that wonderful pairing, that's going to improve in the future and provide a lot of leverage.
I like the idea of anything that can do that. As you might have seen if you didn't blink, I was showing some change detection imaging from the rovers. And one of the problems is if you try and do subdiurnal imaging, then you have a lighting difference. So then you're really trying to you're basically trying to get some rock in the image so that you can see whether the sand is moving onto or off that rock surface. So it kind of becomes just a lot harder to be able to tell in detail where the motion is happening. But especially if you're lacking a wind sensor and you're trying to use the change detection to tell you what the winds are doing as well, it just becomes really hard to get anything other than this happened at some point during the day. So I think to have something that could be, doing a really fine job of that topographic change detection at that kind of small scale. I'm not familiar with that, but I'd love to hear more about how it works on Earth at a in situ location. And as Jack said, ingenuity and future rotorcraft would be really exciting for that on Mars and Titan and other places.
In the room, Alejandro, and then Steve, I see you.
So I just wanted to move this on to a slightly different topic. Ed mentioned the hydrological cycle on Mars, but to make this not just so Mars specific, I think one of the key investigations for planetary in situ measurements is understanding the exchange of volatiles between the near subsurface and the near surface atmosphere. Whether on Mars, that's exchange of water vapor on a diurnal cycle, or whether on Titan, that might be the exchange of methane and ethane into the subsurface or not. Whether that even happens or not, I'm not entirely sure. And it doesn't have to be as a vapor. I don't think it could be also exchange in the liquid phase. And I think one of the nice things about framing it this way too is this brings in a lot of different measurements, because you want to understand wind measurements, but you also want to understand atmospheric composition measurements, surface composition, a whole bunch of stuff. So I think that's a key thing that is not just a planet specific question.
And sorry, Steve, go ahead.
This is probably a comment best made at the end of this whole workshop. Once the various measurements that all of you who are more tuned into the Mars conditions than I am are coming up with, once the wish list is developed. But we go to so many, various teams are going to so many awesome places around Earth to look for analogs, and field work is really expensive. It would be ideal if we could add on a few sensors to each of our own projects that could fill other people's needs as we go to these exotic and distant locations. So, I mean, just a thought that if adding a few sensors, a few extra data channels might produce data that could feed into, I don't know, a pool situation that serves other people, that would be nice.
We have a hand in the room.
Hey, this is Christy Swan. So one thing that I am, and that we've been talking about for, I feel like a number of years at this point, is really trying to characterize the boundary layer. And I think that ties into what Alejandro is saying, but without understanding what those dynamics are, and if the law of the wall actually holds true when you have such strong convection because of the temperature differences. I think we really need more than one anemometer. I've been wanting that for a long time. So I think many people have. So I think if we can characterize the boundary layer, the internal boundary layer, and then somehow relate that to the models, so get some kind of observation at a height where we can do something where we're coupling it with some larger scale atmospheric model.
And with more anemometers, they might last longer on these missions too.
I mean, I think by definition, the anemometers need for that, whatever is in them that is sensing the flow needs to be exposed to the flow without any protection. And so that, I think, means that we need to have anemometers that where the sensing area does not have electronics in it that are fragile and that are going to be affected adversely by grain impacts. And so I think, for me, that's pointing it towards something like the sonic anemometers, which then, they give you the opportunity then to do those really high frequency measurements and the full 3D measurements, and also to couple with, if you measure the temperature as well, then you get the sensible heat flux. If you're measuring, water vapor with a tunable laser spectrometer that's coupled with it as well, or something like that, then you get the water flux in and out of the surface. So I think, we can keep sending more anemometers, and we can keep sending, try and put various protections on them. But I think until you take that, until you actually make the space that is that you're needing to keep pristine for the flow to be undamaged, and then you actually have that be air with sound wave going through it or something like that, I don't think you're going to have you're not going to have that confidence that your wind sensors aren't going to be damaged by the very thing you want to measure.
So these are, just to chime in, these are great points. And we're kind of sliding into the second part of the discussion that talks about sort of challenges and complexities associated with both planetary and potentially sort of investigations. There's a couple other comments just to highlight here. I think Derek Jackson mentioned particle size distributions as well, Serena, that I caught. Oh, and then CO2, which you've grabbed as well, associated with exchanges between atmosphere and surface. Great.
Any last comments? Otherwise, of these, let's down select to about 4, because that's how we're going to divide up into breakout rooms in the next session after a short break. So one thing I'd poke at, I think the Titan one is an excellent one, but do we have the expertise to have a good discussion about that? I'm looking at Jane. Okay, those online, do we have folks? Janie declined to be our resident expert on it. Those online. I don't know if Ralph is still on.
Can you repeat the question?
There was a suggestion of talking about Titan's organic phase states and equivalence to a hydrological cycle as one of the investigations. We would then talk about how would we make those measurements. But if you're our only expert, I kind of feel like you'll just be talking to yourself mostly. Okay, so good to hear Ralph is online, but if nobody else, oh, he's not here. Sorry. Okay, so I suggest we drop that one as one of our small group discussions. Again, Cynthia, it was a very, very interesting topic. I just don't know that we can have much of a discussion on it. Jack.
I guess just to maybe add something in terms of particle size distributions, you can also, that's also an important component of the dust that's lifted. So I think it'd be really good to spark some conversations on potential instrumentation to go at particle size aloft. And now we have a tool that might be able to do that.
Great point. Okay. We still have 6. Subsurface signatures of subsurface volatiles also sounds really interesting. Certainly that lends itself to in situ measurements, but is it in situ process observation measurements? Otherwise, I'm going to suggest moving that one off. Tim's got a comment.
Perhaps you could lump the surface signatures of subsurface volatiles with the understanding volatile exchange. Because I think of that layer between, ground and air, and, that's the boundary, and a lot of stuff happens on both sides.
That makes sense. Okay, and then the other one that's very open is the atmosphere and surface atmosphere interaction models. Don put that in. I imagine he was thinking about more the atmospheric focused. Can we make that more specific? Do we want to tie that in with surface roughness? We need one more to come off the list.
I think, the surface atmosphere interaction models could go with the understanding volatile exchange, perhaps. I don't know. And it's all related, right? But I think Don, I think your key point was just getting the data that can test what we have in the models to make sure that the models are actually improving.
Yeah, I just tossed in surface atmosphere interaction to not be too parochial about it. And what Claire said is what I had intended. At least that was what I thought is the key thing.
I think it's a good point.
I would think that statement about validating surface atmospheric interaction models, it's like there's so many things you could be talking about in that particular case. I mean, there's a lot of different models. And so it's, that could almost be something to ask in each of the four subgroups.
Yeah. Okay, so it sounded to me like it was kind of included under the others, so I'm going to take that out. So we have dust lifting, some focused on kind of surface roughness, and so that is an interaction between the atmosphere and the surface, volatile exchanges between atmosphere and surface, and then aeolian flux measurements. This one is more focused on sand. We good with those four? Okay, so when we come back from break, this is going to be number 1 for you online folks, number 2, number 3, and number 4. And you in-room folks divide into 2 to 3 groups and pick whichever ones you guys want to talk about. But the online folks will do breakout rooms and number it that way. All right, we're a little over time. Let's go ahead though and take a 10-minute break, and we'll just eat a little bit into our small group discussion. But thank you all. Yeah, so in 10 minutes, we'll open the breakout rooms for the online folks, and in here, we'll have people self-organize. Remember that for small groups, make sure you find somebody to help kind of keep track of key points.